Welcome one, welcome all. How are you guys today? I'm glad to hear it. I hope you guys are well. I hope this does nothing to change that. It is Tuesday, our second happiest day of the week. We have started discussion of Einstein's special relativity. So I wanted to start doing some example problems. We'll do more in lecture, and we'll also uncover more aspects of relativity as we go along. But I wanted to start with some problems that are largely based on the Lorentz transformations, the velocity transformations. I'm trying to think if I included some time dilation or length contraction problems in there, but I guess we'll see what I wrote on the board. I can't remember right now. Just as a quick rehash, if we have, for starters, two frames, S and S prime, S prime is moving in the plus x direction, and S measures the speed of S prime to be v. Coincidentally, or not coincidentally, I suppose, S prime would say that S is moving in the negative x prime direction with speed v. Then the Lorentz transforms give us the ability to compare measurements the same way the Galilean transforms did. And so we could say that to go back and forth between measurements in the unprimed and the primed frame, x prime is equal to gamma times the quantity x minus vt. Y prime is y, z prime is z, t prime is gamma times quantity t minus vx over c squared. Now's a good time to state that gamma is 1 over the square root of 1 minus v squared over c squared. Sometimes you'll see this written, because I'm lazy and I try to shorthand as much as I can, sometimes you'll see this written as gamma is 1 over the square root of 1 minus beta squared, where beta is v over c. You could also transform from measurements in x prime to x. Note that all we're really doing is we're flipping the minus signs. The velocity transforms actually extend directly from these Lorentz transforms, and I'll cover that in lecture, just so that I'm not duplicating videos here. But I'll just say that if S and S prime both measure the velocity of a particle, then the velocity, the x component of the velocity in the primed frame is the x component of velocity minus v over 1 minus v ux over c squared. Again, this assumes that v, the relative motion between the two frames, is along the x prime axes. Note that in the Lorentz transforms, x and t undergo changes, but y and z don't. I do want to note here that that we have to be careful. We can't just say that uy prime is uy here. Uy prime is uy over gamma times quantity 1 minus v ux over c squared and quantity. And similarly, uz prime is uz over quantity, uz over gamma times quantity 1 minus v ux over c squared and quantity. So even though this is z, z, this one's x, even though this one's y, y, this one's x, right? Because V is along this x direction. And it has this effect on t. Yay?
Yeah.
Okay. So, and I guess there's a couple special cases of things that pop out of these Lorentz transforms that I'd like to emphasize, but what I will tell you is that if an observer sees both events occur at the same location, that observer is measuring something that we're going to call proper time. Proper sometimes connotes like better, the way it should be. I don't want to mean that. I think that this really originates from a kind of impractical translation of own or self. So, it's a very useful time interval between two events, but I want to be careful here to stress that it's a special case. That doesn't necessarily make it the best case, right? Or the only case. So here I'll say that some time interval that isn't the proper time interval is equal to the proper time interval divided by the square root of 1 minus v squared over c squared. And so delta t is equal to gamma times delta t proper. Similarly, there's length contraction. So an observer who is at rest with respect to the length of the thing being measured will measure the proper length. And again, proper here I don't mean to connote better. It's a special case. But there, any other length measurement made in a frame that isn't capable of measuring the proper length is going to be the square root of 1 minus v squared over c squared, that quantity times the proper length, the length measured by someone who can measure the length of the thing while it's at rest with respect to them. This, by the way, is also equal to the proper length over gamma, right? Is that all right?
What is gamma?
Gamma is this 1 over the square root of 1 minus v squared over c squared, where v represents the velocity between the two frames of reference, and presumed along the x-axis in these equations. Okay?
So what does proper? Proper means that the stuff doesn't move, is there or?
No,
Or means correct? Or means
I don't want it to mean correct. So the proper time is measured by someone who sees both events occur at the same location. So
like yes.
I'm gonna mess this up, but I'm gonna start walking at a constant velocity, and I'm gonna throw the pen up in the air, and I'm gonna catch it.
Okay, I
So-
want you two events. You
So
working and
the-
you.
Well, so the two events are the pen leaving my hand and the pen coming back to my hand.
Oh, okay.
So let's watch again. So pen leaves my hand, pen comes back to my hand. Those are the two events. For me, those two events occurred at the same location, right here. For you, you saw one event occur leaving my hand here, and you saw it coming back to my hand here.
Yeah.
So you did not see the two events occur at the same location, and so you're measuring a delta t. I see the two events occur at the exact same spot, right here, like this far in front of my face, right? So for me, I'm measuring a proper time interval there.
Got it.
The proper length is measured by someone for whom the thing being the length of whatever is being measured is at rest with respect to you. So you can measure the proper length of the whiteboard, right? It's not moving.
Yeah.
But if I am moving, I'm measuring L, you're measuring LP.
Oh.
Does that make sense?
Yeah.
Okay. So let's put some of this to practice. I'm probably going to regret this first problem as a choice because there were easier versions of this that I could have started with. But let's jump in the deep end of the swimming pool. So we have Earth, and Earth observes two cosmic ray protons traveling towards Earth from either side, two particles traveling directly towards it from opposite directions. Particle 1 is traveling towards Earth 60% the speed of light in the, let's let the x-axis, I don't know, be doing that. Yay?
Yeah.
Particle 2 is moving at minus 80% the speed of light, right? Minus 0.8. So that just says it's moving the negative x direction.
Yeah.
Yay?
Yes.
At 0.8 c. We're happy?
Yeah.
Okay. So the first question I want to ask is, what velocity would particle 1 measure for Earth? What velocity would particle 2 measure for Earth? And so for this, I come back to this idea, right? I said that S sees S prime traveling V in the plus x direction. What would S prime say about S?
So S prime say S will go to the left, that way.
So S prime says that S is moving to the negative x direction with speed V.
Mm-hmm. Yeah.
Okay, so let's apply that here. For particle 1, Earth says that particle 1 is traveling in the plus x direction, 0.6 c. What does particle 1 say about Earth?
Then S should be say in the opposite way, so in your left hand.
So particle 1 is going to say that Earth is traveling minus 0.6 c. Yeah?
Yeah.
What is particle 2 going to say about Earth?
Maybe say it's moving positive 0.8 c.
Yep. Plus 0.8 c. That makes sense.
Yeah.
Okay. Now let's get to the part where this gets a little trickier, right? So now we want to say, what velocity would particle 1 measure for particle 2?
They are different location. They both are moving. Is it just add? Just 0.65, 0.8?
So if I added 0.6 and 0.8,
Oh, no, not that. Should be minus, subtract further.
well, are they getting closer to each other or further away?
This are close to each other, right? They move.
So-
go around, or you mean just go this direction? This go this go.
So I guess what I'm asking is, what velocity would particle 1 say particle 2 has? And we can't just say it's 1.4 c. It can't be greater than c. We've never observed a particle traveling greater than the speed of light.
0.2 c.
Well,
Negative 0.2 c. No, still wrong.
yeah, that doesn't work either, right? So let's apply our velocity transforms. And so for this, our standard approach is going to be that we should name the different frames. And so I named the one on the left S prime, and I named the one on the right S double prime. This worked out nicely for my memory too, because 1 goes with 1 prime, 2 goes with 2 prime. But we can't always do that, but this time we can. So let's see if we can make this go. So let's say that we want to measure the speed of particle 2 as measured by particle 1. And so we're going to say that u2 prime, right? So the way I read this is the speed of particle 2 as measured in the 1 prime frame. Yeah? And so this should equal, by our rules, u2 minus v over 1 minus v u2 over c squared.
Okay, that makes sense.
So let's plug in values. So what is u2?
U2 is 0.8 c.
Minus 0.8 c?
I think U just means speed, right?
Yeah.
If it's speed, then I don't need the negative sign, right?
Oh, here we need negative
Oh, we
signs.
need?
Yeah,
Oh.
we need to keep track of whether it's plus or minus.
Oh,
So maybe what I'm saying is closer to a velocity than... So what's v here?
2.6 c.
Yep. Plus or minus? It's plus. Yay?
Yeah.
And then 1 minus, you just told me v was 0.6 c. u2 you told me was?
Negative 0.8 c.
And so the numerator becomes minus 1.4 c.
Yeah.
The denominator 0.6 times 0.8 is 0.48.
1 plus 0.48.
And then c times c is c squared, divided by c squared is 1.
Cancel.
And so we have minus 1.4 c over 1.48, which minus 0.9459 c. So I'm just going to call that, I'm going to round to 0.946 minus. Okay, so what if we want, what velocity would particle 2 measure for particle 1? There's
Flip the sign, right?
There's a trick that we can play, right? It's the same thing we did here. We could say that if Earth says particle 1 is traveling at 0.6 c, particle 1 must say Earth is traveling at minus 0.6 c, right? That's what, so we know that this answer has to wind up being about plus 0.946 c,
Yeah.
but let's pretend we didn't see that trick.
Okay.
And so let's set up another one of these equations. So help me write this one out. Well, this is going to be u1 double prime is equal to u1 minus v over 1 minus v u1 over c squared. Okay, so let's plug in values. What's u1?
0.60.
0.6 c. What is v?
Negative 0.86.
What is v?
Negative 0.86.
What is u1?
U1, 0.60.
Excellent. Really good job. And so now we get 0.6 minus 0.8 is still plus 1.4 c over, well, we already did this, 0.8 times 0.6 is 0.48. So that's,
Yeah, 1.48.
since we already did this, I'm going to assume that this is just 9459c, which makes this plus 0.94. Oh, let's round the same so that. Yay?
Yeah.
Did that work?
Yes.
Okay, good. All right, so let's try another one. This is me I want to be careful. This is me stealing a little bit of extra time to introduce a topic that I wanted you to see anyways. And so here I'm giving you 4 particles. Oftentimes it's going to be useful for us to keep track of time in units of meters or distance. And I know that that seems weird, but since we have that v is equal to delta, well, let's say that v is equal to delta x over delta t, well, we could say that v times delta t is equal to something with length, right? And so we're going to measure time in this weird unit of c times delta t, or c times t. So we have 4 particles. All of these describe their motion, particle 1, particle 2, particle 3, particle 4. All of these describe their motion over some time interval equivalent c delta t equivalent to 3 meters. And so, by the way, well, I'll do it in a second. I'm getting ahead of myself. So, if I wanted to kind of plot our particle's path, particle particle 1 just sits there, right? And so I don't know, I'll call that 1. That's not too confusing?
Yeah, it's okay.
Okay. I'm assuming these all had constant velocities to get from where they went. Particle 2 went 1 meter in the negative direction in that same 3 meters of delta CT. So particle 2 did that. Yay? Particle 3 went to 1.5 meters in that same time interval. That's all right? And then particle 4 went three meters in that same 3 meters of C delta T. Is that all right?
Yeah.
Okay, so what I want to do now, so we often describe these lines as world lines.
Oh, how do you get particle 3 is there? Particle 3 I look is like 1.5. Oh, okay, got it.
So, yay? So we often refer to these as world lines. They're actually very useful. And the thing that I want to point out to you is that buried in this is a statement of the speed of the particle. And so we could say that, let's look at the speed of particle 3. It would be delta x over delta t, right?
Yeah.
So what I'm going to argue is that if you plot CT against x, it is equal to 1 over the slope. So let's check this. So what is delta x here for particle 3?
And then X is just 1.5.
1.5 meters, yeah?
Yeah.
And what is delta CT?
You say particle 3, right?
3 meters. And so let's say that implies delta t is equal to 3 meters over c. Yay?
Yes.
Which c is roughly, for our purposes, 3 times 10 to the 8 meters per second. And so this is 1 times 10 to the minus 8 seconds.
Yes.
Yeah?
Yeah.
So if we wanted to find u then, u3, and it's delta x over delta t, well, we could say that's 1.5 meters divided by 1 times 10 to the minus 8 seconds. That's going to be 1.5 times 10 to the 8 meters per second. Note that this is 0.5 C. Yeah?
Yeah.
What is the slope of this line?
The slope should be the 1 point, oh no, it should be 3 divided by 1.5. It is 2.
So the slope is 2.
Yeah.
I don't know how to write this, but is that's too many 1s, 2s, 3s, and 4s. The slope of this thing is 2. Yeah? What is 1 over the slope?
1.5.
So that says something interesting about particle 4. What is the slope of particle 4?
Still 3 over 3? It's 1.
So the slope of particle 4 is 1.
Yeah.
So 1 over 1, right? Because remember the speed is 1 over the slope. The speed of particle 4 is the speed of light. And so that is going to set the speed limit. In fact, we are usually going to do something like this, where all particles have to have world lines with slopes between these two dashed lines, because it's slower than light. That's the rule. And so we'll do some problems where this helps us out. But is that sort of okay? So the slope of the world line for light is going to be 1. So that could be CT in meters and X in meters. That could be CT in, I don't know, light years and X in light years. It could be, a light year is the distance light travels in 1 year. A light month is the distance light travels in 1 month. It could be inches and inches, right? But this is something that we'll return to time and again. Okay? So here's kind of an interesting bit of relativity, right? Special relativity starts to make the universe look really interesting. So I'm going to tell you that in the S prime frame, 2 events occur at the same location, x0 prime. And the 2 events, as measured by an observer in S prime, is T1 prime and T2 prime. So event 1 happens at T1 prime at location x0 prime. Event 2 happens at time T2 prime at the same location x0 prime. Yay?
Yeah.
Okay. S prime, as we've been saying, is moving with speed v relative to observer in S, the unprimed frame. We want to know how far apart are these 2 events as measured in the unprimed frame. So we're going to turn to our Lorentz transforms. We can pick this guy or this guy if we want. Since we know the stuff in the primed frame, we should use
The red one.
this one, yeah?
Yeah.
Good. So we're going to say that x is equal to gamma x prime plus vt prime. Yeah? Okay, so then delta x should just be our statement for event 1, statement for event 2, right? And so we're going to say gamma times what was the location of event 2 in the primed frame? What is where did the event happen according to, where did event 2 happen according to the primed observer? Happened at x0 prime. And when did event 2 happen in the primed frame? It happened at t2 prime. So delta anything is the later minus the earlier.
Yeah.
And so now let's do this again, but for event 1, right? This is for event 2. So now let's do the same thing, but for event 1. So where did event 1 happen according to the primed frame?
Event 1, 0?
X0 prime?
Oh.
Both events occurred at the same location in the primed frame.
Oh,
And so we're going to add to this plus v times what time did the primed frame measure for event 1?
okay. T1 prime.
T1 prime. Yay?
Yeah.
Okay. Something nice happens here, right?
Yeah.
A lot of this stuff drops out.
Yeah.
So note that we have gamma times x0 prime minus gamma times x0 prime. And so we are left with gamma times v times t2 prime minus gamma times v times t1 prime.
Yeah.
So note that this is just equal to gamma times v times delta t prime.
Yeah, T prime. Yeah. Yeah.
Yeah?
Yes.
But we started today by saying that if an observer measures both events occurring at the same location, that person can measure the proper time interval. Yeah? And so we can say that this is gamma times v times delta t proper. Yay or not yay? This only works because the S prime person sees both events occur at the same location. This was when I threw the pen in the air, I saw both events occur at the same location.
Oh, okay, yeah.
Right? But I can shuffle this around. I can say that this is V times gamma times delta P with no penalty, right? But what is gamma times delta T proper?
It's just delta T.
It's just delta T. Yay? So, if we want to know the distance in the unprimed frame, we'll note that it's equal to v times the time interval between the two events in the unprimed frame. This is kind of interesting, right?
Yeah.
The primed frame says both events happened at the same spot. The unprimed frame says not necessarily, right? The unprimed frame says, in fact, no, if v is non-zero, right? Does that work?
I feel like we still go back to our physics one. You have already told me that x equals v times delta t.
A lot of this is just algebra, right?
Yeah.
There isn't a whole lot of, well, we're about to get to, in lecture, we're about to get to some stuff that is truly crazy. This is already, in my mind, kind of amazing, right? Because the two observers don't see the two events happen at the same, right? But we already saw this, right? I threw the pen up in the air. From my perspective, if the origin of my coordinate system is the palm of my hand, I saw the pen leave my hand at the origin and return to my hand at the origin, right?
Yeah.
But your origin could be where you're sitting, right? And so if the x coordinate is this direction for you, you saw it at one x value and then land at another x value.
Yeah.
And so maybe it's not quite as wild as we might think at first. Okay, so are you ready for?
Challenging problem? Yeah, come on.
All right. So we have a very US-centered view of the Earth. Nothing is meant by this other than I know how often elections happen in the United States. So we have a group of space travelers that vote in the presidential election, and then they immediately get in a spaceship and travel away from Earth with speed 0.75 c. They don't want to miss the chance to vote in the next election. And so they set an alarm on their cell phone or whatever computer for 4 years, 48 months. I know it's not exactly 48 months, but let's pretend. And they're gonna vote absentee. They're gonna radio their vote back to Earth. They already know who they're voting for. They're voting for whoever they voted for this time. They apparently don't care what happens during that 4 years. They're just gonna vote for the same person. So the question is, when is their radio transmitted vote going to get back to Earth? And there's a couple of things going on here. First, we want to think about who gets to measure proper time here. What are the two events? So I kind of glossed over this in my story. They get in their spaceship, they start traveling, they set the timer on their their computer for 48 months. So they set the timer. I want that to be event 1. Event 2 is 48 months later, it chimes and says, don't forget to vote. So is someone on Earth measuring proper time, or is someone on the spaceship measuring proper time?
On the Earth. Oh, in the space.
On the spaceship. Who sees both events occur at the same location?
The person set up the.
So event 1 is right here, the clock turns on, or clock set, alarm set. Event 2